So in the last class, what did we saw? We saw the algebra. We were dealing with algebra of complex numbers. So the operations that we saw was equality, how equality is defined. So part by part, they should be equal. Z1 equal to Z2. Part by part means if it is written in the standard form, so the real part x1, x2 should be equal. The complex part y1, y2 should be equal. After that, addition of complex numbers, it is added again part by part. Real parts are added, imaginary parts are added separately. And, we can see that addition satisfies commutative associative closure. Additive identity, identity is of the complete set of the complex numbers. So complete set of complex numbers, the additive identity is 0, 0 plus I times 0. You see this, that kind of number, which when added to Z, it gives answer Z only. Multiplicative identity, again of the complete set C, when multiplied by Z, the answer should be Z. That is the multiplicative identity. Then additive inverse, these definitions is additive identity, additive inverse. So x plus iy, inverse is additive inverse minus x plus minus iy. Then we saw the definitions of subtraction. So Z1 subtraction, Z2 is to subtract the number Z2 is same as adding the additive inverse of Z2. This was the definition given for subtraction, and we know what is this minus Z2, additive inverse. So that way, we derived that Z1 minus Z2 can be written as, using this proof, we derived that subtraction of real parts, addition, subtraction, multiplication. Now, why this complicated definition of multiplication was given, that also I told you. In order to miss by this complicated definition, our distributive law gets satisfied, so that further work gets simplified. The further properties of distributive law and all those properties gets applicable in complex also. That's why this complicated definition was given. Okay, and then we practice some sums for multiplication, and last multiplicative identity is 1. That's 1 plus I said multiplicative inverse. Now, this is a little bit a tricky concept. So this multiplicative inverse is if multiplicative inverse of a particular complex number. So let's suppose Z1 is there. Z1 it's multiplicative inverse symbol, it is 1 upon Z1. So Z1 multiplied by 1 upon Z1, that means our target is 1. Multiplicative identity is 1. So Z1 multiplied by what is 1? So the symbol is noted by 1 upon Z1. And I just told you that 1 upon Z1, that is multiplicative inverse of x plus iy, will be x upon x square plus y square minus I times y upon x square plus y square. How did I get this answer as of now? And we just verify that whether or not actually their multiplication is 1. This multiplication will verify. X. This is first complex number x addition iy. This is second complex number x upon subtraction I times y upon x plus y, and we multiply like the previous multiplications that we did. This previous multiplication that we did, that will be multiplied. So now you know to calculate 1 upon z. Today we will discuss with deviation of complex numbers. So division of complex numbers. So if let's say Z1 is equals to x1 plus I times y1 and Z2 is equal to x2 plus I times y2, then Z1 divided by Z2, if you want to calculate, it is same as actually Z1 upon Z2 symbolically. Okay, Z1 upon Z2, but right now we don't know what is this Z1 upon Z2. So you may have given the definitions of x1 upon x2 addition I times y1 upon y2, but that definition was not given. What definition was given? The first complex number, let it be as it is, and instead of dividing by the second, you do multiplication by inverse of second. Now which inverse? Not the additive inverse, the multiplicative inverse. The multiplicative inverse of second whatever that number is, you divide by that, you multiply by that number. So this, if we go by substitution of x1 plus I times y1 divided by x2 plus I times y2. This is equal to, sir, x1 plus I times y1 multiplied by multiplicative inverse of x1, x2 plus I times y2. And multiplicative inverse of x2 plus I times y2 is represented by the symbol is 1 upon. So x1 plus I times y1. Sir, what is the multiplicative inverse of the second complex number? This number I have memorized. What thing I have memorized? The multiplicative inverse is x2 upon x2 square plus y2 square minus I times y2 upon x2 square plus y2 square. And after this, multiplication standard operation, again that is also defined. How that multiplication operation is defined? So we will multiply this real parts, sorry, the real part and the imaginary part, so that I and I will get, I square will become a real number. And the distributive, using distributive law, I will also have to multiply this x1 by the imaginary part and the imaginary part of this by the real part. That multiplication. Now that with that multiplication we need a very complex formula that I'm not writing. So we'll just understand this definition, that Z2 Z1 upon Z2. Z1 upon Z2 is defined to be equal to Z1 multiplication with.
Sir, could you just scroll down, sir?
Yes, 1 minute. Divided by Z2 is same as multiplication by multiplicative inverse of Z2. This is the definition given for division. Taken the screenshot. I hope here there should be no doubts up to this point.
Done, sir.
So just evaluate. Six plus 8i divided by 3 minus 4i. Don't memorize the formula. Don't memorize that inverse formula. That inverse formula, I have told you the trick also. Actually, what is division by the second is actually what? 6 plus 8i. Multiplication by inverse of the second. Multiplicative inverse symbol is 3 minus 4i. Now this symbol which is there, multiplicative inverse of the second complex number, my memory is very low. I will not remember formula. Instead of what trick I told you, this is 1 upon 3 minus 4i. Inverse, what is how to remember it is inverse, you just remember something like this. Multiply by 3 plus 4i numerator and 3 plus 4i denominator. This multiplication as such, it is completely meaningless. Multiplication by 3 plus 4i upon 3 plus 4i, but still we are doing it. Here, this second complex number, the numerator becomes 3 plus 4i, and the denominator, can you see that it is actually nothing but 3 square plus 4 square. This is 6 plus 8i. So my answer, the question is 6 plus 8i multiplied by 3 upon 25 plus I times 4 upon 25. This is the only way how we calculate the inverse of the any complex number. Yes or no? You remember this, I hope. Calculate multiplicative inverse. Is to do this thing, multiply by purple upon purple. It's meaningless thing, but it's a trick to remember the inverse thing. Yes or no, students?
Yes, sir.
So once you got over here, now the multiplication, will you be able to do the distributive that we used to do? Starting for the practice purpose, in the starting we can write in the vertical arrangement 6 plus 8i, and this is 3 upon 25 plus 4 upon 25 times I. Multiplication. So the real parts, the final answer, real part of the final answer will be given by this multiplication and this multiplication, vertical multiplication. 6 3s are 18 and 8 4s are 32, but that 32 will be accompanied with a negative sign because we change the sign. 8 4s are 32 and I square becomes minus 1. So 8 4s are 32, I square, that is minus 32. So 6 3s are 18 minus 32. 18 minus upon 25 is already there. Minus 14 upon 25. And after that, for the imaginary part will be given by this cross multiplications. 8 3s are 24 upon 25i, and the 6 4s are 24. 24 plus 24 is 48 upon 25. I times 48 upon 25. This will be the final answer. So you can also write it as 1 upon 25 times minus 14 plus I times 48. Okay. Scroll down. Take a screenshot.
Sir, it's better if we write it as running mode, sir, because taking screenshot then noting it down is a bit difficult, sir.
Told me to take Jita told me I think to scroll down.
So not this one, sir. Evaluate first one, sir. Yes, sir.
While I'm explaining at that time only, you should write. Make that habit. Jita, are you getting it? Till that time, quickly calculate one. Let's one sum for practice.
Sir, done, sir. Till how much you have shown, till there I have done, sir.
Quickly calculate this division.
So can you please scroll down, sir? Done, sir.
Do the second question. Second question division I have given 5 minus 3 I have come 1 plus 2. Quickly. Dhananjay, did you get the answer?
Sir, doing, sir.
Dhananjay, what about you? The time not so much, not take so much time.
Minus 1 by 10 minus 79 by 10. So
No, wrong. 5 minus 3i, it will be 5 minus 3i. The division by second is actually multiplication by multiplicative inverse of that another one, that is 1 plus 2i, and 1 plus 2i the multiplicative inverse, same as 5 minus 3i. I have not memorized the formula, so I will just write it as 1 upon, in fact not memorizing the multiplicative formula is beneficial. It's more benefit. 1 minus 2i upon 1 minus 2i. So loosely can I write the answer as 5 minus 3i 1 minus 2i, and the denominator becomes, so denominator is 1 square addition 2 square. This 1 plus 2i 1 minus 2i, this kind of sums, their answer will always be real part square plus imaginary part square. This question we have done, yes or no?
Yes, sir.
5 minus
Yes, sir.
3i 1 minus 2i upon 5. The numerator multiplication, if you want for convenience, you can write in the vertical arrangement, but don't make it a habit. With practice, you should practice so much sums of multiplication that you should get rid of this habit. So 5 ones are 5, addition 6, but that addition 6 I will change the sign because of I square. 5 ones are 5 and 6 I square, so 5 minus 6. The numerator it becomes negative 1. The cross multiplication of the imaginary part is negative 10, negative 3. Negative 10, negative 3 is minus 13 times I
Excuse me, sir.
upon 5. Yes, tell me.
Sir, how can be 1 square plus 2 square become like positive, sir? There will be minus sign in between them, right, sir?
No, it is actually 1 plus 2i and 1 minus 2i. So it is 1 square subtraction 2i complete square it is.
Sir, can I show you what I have done because I have a bit doubt. So
1 minute. The denominator is 1 plus 2i and 1 minus 2i. It is something of the form p plus q, p minus q. Okay, first do by the standard method. So what is the standard method? Thus a distributive law that we use. 1 into 1 and then subtraction minus 2i whole square, yes or no? After
yes, sir.
and by the cross multiplication that we will do, 1 into 2i, 1 into 2i. They will have opposite signs, so they will cancel out. So there will be no imaginary part of I. Do you agree, Afrin? And this will
Yes,
be
sir.
1 minus, what is 2i complete square? 2i complete square is always a 2 square and I square. I square will be negative ones. That negative one, shall I make it over here? Plus 1 minus 2i whole square is what? 2 square I square. 2 square I square. And I square is negative 1 now. 1 minus 2 square into negative 1. So 1, 2 square and that negative 1 is coming and bringing it plus. Got it, Afrin?
Yes, sir.
5 minus 3i, 5 plus 3i. Do it. It will be 5 square addition 3 square. Actually, original it is 5 square minus 3i complete square, and it is 5 square minus 3 square into I square, and I square it becomes negative 1, so 5 square plus 3 square. So now this is the final answer. Minus 1 minus 39 upon 5. Okay.
Yes, sir.
Yes, very good, Pujita. Pujita got correct. Dhananjay got the wrong answer. Some calculation mistakes in it. So now in multiplication, this is the division. You got understood the division. We'll practice some more steps after that. After this also. Multiplication, just verify one thing: the various properties of multiplication that I told you. It will satisfy commutative, associative, distributive, and all those things. Closure property, multiplication, commutative, associative. This is already there. For associative, I told you to verify yourself. Z1, Z2, Z3. That first that multiplication, then multiply by Z1. And the RHS is first take Z1, Z2 multiplication. Whatever answer you get, that you multiply by Z3. This was given as a homework, nothing difficult. By distributive law, whether this multiplication involves this, whether distributive law is true for multiplication of complex numbers. How to verify that I will tell you. That part I will leave as a homework to verify. Verify yourself that distributive law is hold true in multiplication. Z1 times Z2 plus Z3 is in fact Z1, Z2 addition Z1, Z3. So just take three complex numbers: A plus I times B, C plus I times D, E plus I times F. So what you have to verify? So LHS will be something like A plus I times B multiplied by, what is my addition will be, C plus E is the real part, and I plus I times imaginary part is B plus F, not I times B plus F. So this is my two real parts. This is my two imaginary parts. Multiply them, you will get some answer. Z1 into Z3, Z1 into Z2. So that will be RHS. That you can verify. Z1 into Z3, Z1 into Z2. Two complex numbers you will get. Add them. You will get again some real part and some imaginary part. Check whether this whole thing is one complex number. This whole thing is another complex number. If at all they are equal. Now, how to check whether they are equal? The final real part which you will get, it will be a very, very long expression. The final real part should be equal. The final imaginary part should be equal. If that is true, then this distributive law, we can say that distributive law is satisfied. One property, I leave it to you. I think you can verify yourself. You should. It's not possible.
Yes, sir.
So much time class time in this property. If you are able to verify this property, this is the distributive law in multiplication of complex numbers. So multiplication of complex number. Distributive law for multiplication of complex numbers. Now, since we know now, once we have verified this property, now we know this result, that this result is true. So lot many results of algebra, the algebraic expressions that we had, those can be applied in terms of complex numbers also, algebraic identities. Like in school times, in school days, we studied something like P plus Q whole square. It was equals to P square plus 2PQ plus Q square. While writing this identity, means by proving this identity, make sure now I'm giving a slight hint of matrices also. But to prove this identity in terms of simple real numbers P and Q, what procedure we followed, sir? We did P plus Q into P plus Q, and then we multiplied it term by term. P multiplied by P plus Q. Let me do it complex only. Z1 plus Z2 whole square. So it will be what? So Z1 plus Z2. Basically, it is what? So repetition of the bracket. 2 times repetition of the bracket. Now, since we know that distributive law is satisfied, we have already proved that, we have already verified that result, that distributive law is satisfied in terms of complex numbers. So Z1 multiplied by the second bracket addition Z2 multiplied by the second bracket. Again, the distributive law Z1 into Z1, that is Z1 square, Z1 Z2, then it is Z2 Z1 Z2 square. Now, since these middle two terms, they are one and the same thing, because of commutative law, at each and every step we are using some or the other properties of multiplication, because the middle two terms are one and the same. That's why you can write 2 times Z1 Z2. If the commutative law wouldn't have been true, then we wouldn't have reached at this conclusion of the identity. We cannot have applied this identity in terms of complex numbers. Now, in matrices also, multiplication of matrices is defined in some way. We will see that afterwards. But in matrices, matrix A multiplied by matrix B and matrix B multiplied by matrix A need not be equal. In fact, both of them will be defined. This is also not the case. Both the multiplications will be defined simultaneously. This is also not the case. And if at all they are defined, both the multiplications, even after being defined, whether they will be equal, it's a big question mark. So commutative, sometimes they may be equal, sometimes they may not be equal. So commutative law is not satisfied in general. So in terms of matrices, we cannot say that A plus B whole square equal to A square plus twice AB plus B square, because AB plus BA we cannot do the addition. It's twice AB. Okay. So here in complex numbers, we don't have such trouble. All those laws are satisfied properly. So since this law was satisfied, means we saw the proof. In the proof, we saw how the distributive, so we're basically using distributive and commutative law. So all other identities that we studied for the pure complex numbers, they are satisfied for for real numbers. They are satisfied for complex as well. So the first identity is Z1 plus Z2 square. Second is Z1 minus Z2 square, or I will write here only Z1 plus minus Z2 square, Z1 plus minus Z2 cube. You will be able to calculate these values. No doubt, it won't be trouble. Or shall I write these identities for you? Z1 plus Z2 multiplied by Z1 minus Z2 will be equal to Z1 square subtraction Z2 square. Whether these identities are clear to you, same as the one we used to do for real numbers. Shall I directly jump to examples on these identities? We will practice these identities directly by using examples.
Yes, sir.
Okay. So evaluate. Question number 3. 2 plus 3i, its square. we will do, this is something of the form a plus b. This is my a, this is my b. Okay. So it will be something like 2 square addition 2 multiplied twice ab. Twice ab is 2 times 2 into 3i, and then 3i complete square. Now halfing 2 square and 3i complete square. It will be 2 square minus 3 square. So it will be 4 minus, and then 2 to the 4 is a 12i. So the final answer will be negative 5 plus 12i. Okay. Pujita did that mistake. It will be 4 minus 9 Pujita. Okay. Evaluate 1 plus 2i complete cube.
Sir, answer is minus 7 plus 89.
Okay, so let me write the answer. Addition to a cube plus b cube. Now here, so because we have some problem with respect to I, sometimes it becomes a real number, sometimes it becomes a complex number with related to power. I raised to suitable power, it is a real, and I raised to some, let's say, odd power, I cube, I5, it's a complex. So 3 times a square b. So 3 times a square b plus 3 times a b square whole square plus b cube 2i complete cube. Now the imaginary numbers, the imaginary part, the parts that will come in imaginary, I will underline by purple. So 3 times 3 into 1 square into 2i, this will become in the imaginary part, and 2i whole cube, this will come under imaginary part, and the other will be coming in the real part. So 1 cube and 3 into 1 into 2i whole square. This is 3 to the 6, 6 and I square. So this is negative 6. So 1 minus 6, and here it is 3 to the 6i plus 8i. So it is 6i plus 8i minus 5 plus 49. Okay. Is it clear? After Pushita Dhananjay. Just add.
Yes, sir.
Okay.
Yes, sir.
A cube 3a square b plus 3ab square plus
Yes.
b cube. That was the only identity that I used. One last sum on these identities, and then we will move on to some complex questions, complicated questions. 1 minus 3i complete cube. Quickly answer.
Sir, one scroll down, sir.
Simply a minus b complete cube. So a minus b complete cube is a cube minus 3 into a square into b. That is
3i plus 3 into 1 plus 3i square.
minus b cube. So minus 3i complete cube. The imaginary parts I will underline. This will come in the imaginary part. I will survive over there and I will survive over here. I raised to odd power, the I will survive. I raised to even power, it becomes a real number because I square is negative. So this becomes I cube is 1 and this is 3 square is 9, 9 3s are 27, but 27 with a negative sign it will be. So minus 27. Okay. And the purpose that will be there, that is 3 3s are 9. So it is negative 9i and here it is 27 I cube. So I cube which is there. So, so this is minus 27 now I cube. I square will be what, sir? I square will be negative 1. So that negative 1 I will make over here and then 1 I is remaining. Out of I cube, 2 i's I made negative 1 and 1 I is remaining. So the final answer is minus 26.
Sir, how did we get
How did we get?
27i at the last?
It was minus of 27 I cube, correct?
Sir, after we get 1 minus 27, minus 3i cube. So it will be 27i cube. Sorry, 27i.
27 I cube it will be, na? 27 multiplied by, originally it was 3i complete cube. My second term is a minus b. If I compare it with a minus b whole cube, my a minus b, the b is complete 3i, na? So you will have to take 3i whole cube, na? Here. In the second step, it is 3i bracket cube. Here I have written 3 cube into I cube. 3 cube is 27, I cube is I cube.
So, sir, then from where did we get this 9i?
9i I got from here. This term is my 9i.
Okay, sir.
It's a 9. 9i is that term, and this 27 is from here.
Okay, sir.
Okay. And the 27 I cube which is there. So minus 26 minus 9i. Now this is minus 27. That I cube I will write it as I square and I separate. I square separate, I separate. And this I square can whether I can write it as -1.
Yes.
So that -1, it will change the signature. So -26 -9i, it will become here plus 27. That I square made it plus, and here it is I. Okay. So -26, 27 minus 9 is 89. Got it?
Yes, sir.
Sir, one more sum, sir.
Oh, okay, next. A cube minus 3 into a square into b plus 3a into b square minus b whole cube. So the terms that will come under imaginary, that will where I will survive. I'm underlined with purple. So it will be 27 and 3 3s are 9, 9 4s are 36. So 36 with a negative sign it will be. Okay. After that, minus 9 3s are 27, 27 2s are 54 times I. This term I have calculated. And these are 27, these are 54. And the last term is minus 8i cube is actually plus 8i. This is minus 9 minus 54i, and so minus 8i and I square. So I square will be negative 1. So let's change the signature. So the final answer is minus 9 minus 46 times I. Okay. Okay, clear, Pujita? Dhananjay answered it correctly.
So could you please scroll down, sir?
Pujita, over.
That's
Okay, next question. Express the following in the form a plus ib. Okay. Yes, very good, Dhananjay. Correct. No, Pujita, wrong. That upon 5 that we are getting, that is correct. But numerator, slight mistake. So it is something, sir, 1 minus I complete square, whatever that complex number it is, divided by 2 plus I. Divided by 2 plus I means actually multiplication by 1 upon 2 plus I. Now multiplication by 1 upon 2 plus I is, now this is 1 minus I whole square. Multiplication by 1 upon 2 plus I. The trick to find the inverse is, so just multiply through this meaningless step. The meaningless step is multiply and divide by 2 minus I, 2 minus I. Now I can calculate this value. 1 minus I complete square 2 minus I, and the denominator will be something like 2 square subtraction I square, 2 square minus I square, so it is 2 square plus 1 square. Okay, Afreen, moved out in the denominator.
Yes, sir.
Okay. The numerator, the first which is there, first bracket is 1 complete square. Now I will directly use the identity a square. So a square is 1 only, plus b square. B square is what, sir? A square plus b square. B square will be I square. So 1 plus I square. 1 plus I square is negative 1. So a minus b whole square. So a square plus b square minus 2 times ab. 2 times 1 into I. So it will be minus 2i. I wrote the expansion directly. Okay. No doubts. And this will be upon 5. So it is actually negative 2i multiplied by 2 minus I upon 5. So just using distributive law, negative 2i into 2 is what? It will be negative 4i. And negative 2i into negative I. So first they give plus times 2 times and then I square. So I square, just change the signature, plus 2 and then again I square. So change the signature, whatever you got. So I will just write here minus. And the upon 5 is already there. Got it? That's my answer. I got the answer now. It's just minus 2 upon 5 addition I times negative 4 upon 5. Okay. So no. No doubts.
No, sir.
No, sir.
1 upon 1 minus 2i plus 3 upon 1 plus I 3 plus 4i upon 2 minus 4i. This is one subject expressed in the form a plus ib. Dhananjay, it should be a plus sign in between. First complex number, first bracket will be so just doing the cross multiplication, it will be 1 plus I addition 3 times 1 minus 2I upon denominator will be 1 minus 2I multiplied by 1 plus I. This complete thing multiplied by 3 plus 4I upon 2 minus 4I. Okay, so this is 3 plus 4I upon 2 minus 4I. Let the second bracket be as it is as of now. Now the first multiplication is 1 plus I, and here it is 3 minus 6I, and the denominator multiplication now I will do in the horizontal manner only. The real part is the real part of the final answer. This denominator I'm talking about. Final answer denominator will be 1 into 1, that is 1, and minus 2. This is minus 2I and I minus 2, but I will have to change the signature. So minus 2 will become plus 2 because of that I square. So 1 and negative will become plus 2. So 1 plus 2 is 3. And for the for the imaginary part of the final answer, we do the cross multiplication, that is minus 2I and I. So minus 2I and I is minus 1 times I. Got it till here? And this is 3 plus 4I upon 2 minus 4I. So here it is 4 minus 5I. The first numerator. The second numerator is 3 plus 4I upon the first denominator is 3 minus I, and the second denominator is 2 minus 4I. So the numerator multiplication again, the numerator I'm talking about, the real part of the final answer. Straight multiply 4 3s are 12 and negative 20. 12, but that negative 20 I will change the signature. So plus 20. 12 and plus 20 is 32. And for the imaginary part, minus 15 plus 16. Minus 15 plus 16 is plus 1 times I upon the real part of the denominator. Denominator final answer. 3 2s are 6 and negative 1 and negative 4 is plus 4. So 3 2s are 6, that 4 plus 4 I will have to change the signature. So 6 minus 4 will be 2, and for the imaginary part, cross multiplication, negative 2I, negative 12I. Negative 2, negative 12 is minus 49. I hope up till now I have done correctly. Dhananjay, is the answer matching up till this stage? My answer.
Yes, sir.
After this, I will just multiply by 2 plus 49, and in the numerator also 2 plus 49. Okay, so now the numerator is something like this: 32 plus I 2 plus 14I. And the denominator is 2 minus 49, 2 plus 49, so it will be 2 square plus 14 square, means minus 14 square I square, so it is actually 2 square plus 14 square. So 32 to the 64. 64 and that 14 will become subtraction. So 64 minus 14 is the real part, and the imaginary part will be 2i, and 32 into 14 I will have to do. 14 to the 28, carry 2, 448. 2i and 448i. So that will be 450 times I. Okay, and this complete divided by 200, 196 plus 4. So this becomes 50 plus I times 450 upon 200. From the numerator I can take 50 as common. It becomes 1 plus I times 9. The denominator is 200. Did I do something wrong?
No, sir, correct, sir. 50 and 200, we cancel it.
It's correct, sir.
1 plus 9 I by 4, so 1 by 4 plus
1
9 I by
upon 4 plus I times 9 upon. This will be the final answer. Okay. Pujit also got correct. Very good. This was for the application of multiplication identities and all those things. Next. In your class, trigonometric functions have been completed. So for your class, I can definitely give the sum. 1 upon 1 plus cos theta minus I times sine theta, expressed in the form of a plus ib. Obviously, the answer will be something, means the real part will be some of function of theta, and the imaginary part also will be some function of theta. Are you getting it, students? See here, the real part of the denominator, whatever complex number is, the real part is what? 1 plus cos, this complete is my real part. Are you getting this? And my imaginary part is minus sine theta. The imaginary part, we don't say I, it's just minus sine theta. So with what I will have to multiply, this is 1 upon means x plus iy. X is 1 plus cos theta. This is negative sine theta. This is something like x minus iy. So we multiply by x plus iy. Yes or no? X minus iy we multiply by x plus iy. So x plus iy I will have to multiply by 1 plus cos theta addition plus I sine theta 1 plus cos theta addition I sine theta. This meaning is step that we used to do. Okay. First step clear. The numerator will be 1 plus cos theta plus I times sine theta upon this is 1 plus cos theta whole square minus sine theta square I square. So it will be plus. Always it is x square plus y square. Clear till this point? So this will be 1 plus cos theta plus I times sine theta divided by, do the expansion. 1 plus cos complete square is 1 square plus 2 times cos theta plus cos square theta, and the sine square is already there. So it is numerator is 1 plus cos theta plus I times sine theta divided by the denominator, that cos square plus sine square is 1 and 1 plus 1 is 2. So 2 plus 2 cos theta. Clear up till this stage? Everyone?
Yes, sir.
Cos square plus sine square is 1, that I did. Your identity. 1 plus 1, 2 and 2 plus 2 cos theta. So from the denominator also you can take 2 common. So the real part is, so the real part of the numerator. Now the denominator completely we have got in terms of real numbers only. This is 2 times 1 plus cos theta, and this is I times sine theta upon 2 times 1 plus cos theta. So the real part of the final answer, real part is half and the imaginary part is sine theta upon 2 times 1 plus cos theta. How many of you got correct? Anyone? Did you realize the first step before me answering, before I answered? Did you realize the first step that I will have to multiply by 1 plus cos addition I sine 1 plus cos addition I sine?
No, sir.
Anjay, you also did not get?
Sir, I thought 1 plus cos theta is sin square theta, I wrote, sir.
Yes, I too wrote the same, sir. I wrote as sin theta and then I just went on, sir.
1 plus cos you wrote as sin square theta.
I wrote as 1 plus cos theta will be sin theta, sir. I like substituted the value, sir.
1 plus cos equal to sin. That sin square theta, that identity, that mistake I can accept. Why I can accept that mistake? Because cos 2 theta is equals to cos square theta minus sin square theta. Cos square, if I substitute by 1 minus sin square, it becomes 1 minus sin square minus sin square is 1 minus 2 sin square. Here, and another is, sir, if I substitute this sin square, if I substitute by 1 minus cos square, this becomes 2 cos square theta minus 1. So 1 plus cos or 1 minus cos, they have a relation. 1 plus cos 2 theta. So in fact, I can write it as 1 plus cos alpha is equals to 2 times cos square alpha by 2, or 1 minus cos alpha is equals to 2 times sin square alpha by 2. This mistake I can accept. I can accept that maybe, sir, we memorize some formulas and that will be made in terms of half angle. Okay, that is acceptable. That's okay, silly mistake. But 1 plus cos equal to sin, this is unacceptable. That's last sum for today. Will it be okay if I take for 5 minutes more? Just one last sum I will do.
So could you please scroll down, sir?
1 minute after. Copy this sum also till that time. Prove that others copy this sum. Prove that three plus 2i upon 2 minus 3i plus 3 minus 2i upon 2 plus 3i is your deviation. Copied question, everyone? Which step you have to copy after?
Yes, sir, this one. Done. Sir, the last part.
Sir, and sum also done, sir.
And some also done, Pujita. What was the final answer?
I got 12, sir.
12. final answer should be 0. The addition is 0.
Yes, sir. Now I got, sir, 0. Answer.
If you have done you can log out, Pujita. It will not be a problem.
Answer.
Last question done.
Yes.
Dhananjay, let's write the explanation today. This is 3 plus 2i upon 2 minus 3i addition 3 minus 2i upon 2 plus 3i. So I will think of it as multiplication by 2 plus 3i upon 2 plus 3i. And here it will be multiplication by 2 minus 3i upon 2 minus 3i. So here 3 plus 2i 2 plus 3i upon it will be 2 square plus 3 square addition 3 minus 2i 2 minus 3i upon 2 square plus 3 square. So now 3 2s are 6 and here 6i square. 3 to the real part, first numerator. 3 2s are 6 and 6i square. So it will be 6 minus 6. And I times it will be 2 2s are 4 and 9. It will be 13. I times 13 upon denominator is 9 plus 4, 13. Addition, the denominator is again 13 only. 3 2s are 6 and plus 6 times I square, so it will be 6 minus 6 and minus 13 times I. So 0 plus I 13 plus 0 minus I times 13 upon 13 is 0 plus I times 0 upon 13, which is same as 0 plus I times 0. Okay, so that's all for today. We'll continue tomorrow with the modulus and conjugate. Just 2 parts are remaining. Tomorrow probably this chapter. Have a nice day, everyone. Thank you.